let's do another charged rod problem. We're going to make this one a little harder. So instead of thinking about the electric field here along the axis, we're going to think about the electric field here, sort of perpendicular to the rod and centered on the rod. So let me draw the rod down here so we'll have plenty of room. So here's the rod. Down here. And again, we're going to put the rod on the x-axis like that. And the point P is along the center, so we're going to put the y-axis centered on the rod, just like this, all the way up. Okay? And the point P, we'll say, is right here. That's where we want to find the electric field, to the side of the rod. The rod still has a charge density lambda, and it still has a length L, and we're going to make this the origin so that this is at the point L over 2. And this end is at the point minus L over 2. Okay? So we go from there. It's the same trick. We're going to think of this charged rod as a bunch of little elements dx. So here's one here, dx. And we're going to write dep just like before. So dep, I'll start here. And we just have to start writing it and thinking about what it would be. Here is what we're treating as an isolated charge. Here's a point P. I'll start with the good part, Ke, there. Can do Ke. The charge is dq, but from the last problem, you know we can write the charge as lambda dx. It's just the charge per unit length times the length of the element. So I'll go ahead and write lambda dx here. And now we have to think about the distance. What is the distance from dx to p? Well, we can draw it, sort of a dotted line like that, and see that it's a right triangle. That helps, because we know this side of the triangle, A, we know it's a distance A from the axis, and we know this side of the triangle because we know the x position of all the dx's. Okay? Here it's actually sitting at negative x. You could also have it here at positive x. We're going to think about it everywhere between minus L over 2 and L over 2. So if that's the case, then this length is the square root of a squared plus x squared. Okay? So just use Pythagorean theorem on that triangle. Now, we'll talk about it in a minute when you have to be careful whether you have minus x or plus x, and it can make a difference. Here it doesn't matter, right, because you're squaring the x. So whether you're over here in the minus x values or the plus x values, if you're just getting that length, not an issue because it's squared. So down here, we have to write that thing squared. So basically, the square root goes away. It's over a squared plus x squared. Okay? That's the magnitude of DEP. All right? We have our magnitude. Now, DEP is a vector, and we're solving a vector problem. So when we were getting the electric field at a point just along the length, everything was in one dimension. To make it a vector, we just slapped on I hat because it was in the x-axis. Now we have multiple vector components. We have to think about the fact that DEP is at an angle, and in reality, DEP has an x component, DEPx, and DEP has a y component, DEPy. So we have to separate those. Well, all you really do is say, well, if this is at some angle theta, then this is just DEP times the cosine of that angle. So cosine theta on the I hat, and then we write the magnitude again, Ke lambda dx over a squared plus x squared, and sine theta j hat. So you literally just, you know it's at an angle, so you just break it into two components. It wasn't so hard. We'll have to deal with it in a minute, but that's how you break it into the components. So here we have the full expression for DEP. Okay? Now, we want EP. We want the electric field at point P, so we know we have to integrate. We have to sum up all of our DEPs to get the full field. Let's see then. That means we have to integrate this whole thing. And the limits are going to be what? Minus L over 2 to L over 2. Minus L over 2 to L over 2. Okay. And now we want to write this again. But we want to think about everything in the integral that depends on x. We have to rewrite in terms of x. Okay. So let's see. Ke and lambda don't depend on x. So I'm actually going to make myself a little room and just put those in the front. Okay. Those are in each one. We can pull those out just to make it not so messy. So then we're left with dx over a squared plus x squared. And then cosine theta, though, does depend on where you are. It does depend on x. Because we can think about this angle theta, as we move this around, this angle is going to change, clearly. So we need to get an expression for cosine theta in terms of x. So what we have to realize is that this theta is the same as this theta. Okay? And we look at this right triangle again, and this is how we can figure out what cosine theta is. Cosine is adjacent over hypotenuse, so it's this x value over this hypotenuse value. So cosine theta is actually minus x over the square root of a squared plus x squared. I hat. And it is minus, okay, because it's, you got to be very careful with this sometimes. Here, when we move to minus x, this angle is positive. You usually think of angles as positive from the x-axis. So we go from minus x, this is positive. The cosine of this angle, it has to come out positive, okay, because it's a positive angle. The cosine of a positive angle less than 90 degrees is positive, so we have to have a positive number over this, which has to be a positive number because it's a square root. So when you're over here, the x's are negative, so you have to put a negative in front of it to make the cosine come out positive, okay? There are other ways you could set it up where you wouldn't have to do that. And if you think about it in this case, as you go, x goes positive, what's going to happen is the theta is actually going to go greater than 90 degrees. So that positive negative aspect would work out even when you're over here. So be a little bit careful with your negatives. But for now, the way we've set it up, we stick a negative x there. The j component would be basically the same thing. In fact, I'm going to put a bracket there. It's that same amplitude in front, dx over x, a squared plus x squared, times the sine of theta. And the sine of theta is opposite over hypotenuse. So here there's no plus minus to worry about. It's just a over the square root of a squared plus x squared, j hat. Okay? So now we have everything in terms of x. So we can kind of simplify it a little bit and say now our EP that we care about is equal to Ke lambda times the integral from minus L over 2 to L over 2 of, and now we're going to combine these. This term, first term, will be minus x dx over, and now we're going to combine these. This is really, you could think of it as a squared plus x squared to the 2 halves. This is a squared plus x squared to the 1 half. So when you multiply them, you just add. That's how you get these funny things like a squared plus x squared to the 3 halves. Right? So we just combine those two denominators. And that's on the I hat plus a over the denominator is the same, a squared plus x squared to 3 halves on the j hat. Okay? And the integral applies to both terms. Oh, and you need the dx. They both have a dx, of course. So all we got to do is solve that integral. I've rewritten the integral here to keep us moving along. EP, it's the integral minus L over 2 to L over 2. I went ahead and separated the I hat and the j hat. So this was the cosine component. This was the sine component. So now we have to do this big, nasty integral. All right, well, let's just do it. So EP here on the I hat is, what's it going to be? Well, it's minus Ke lambda. You can always just write down the constants, not a problem. And we're integrating a squared plus x squared to the minus 3 halves. So if we would just want to do that the normal way, that would just become minus 1 half So you would divide by minus 1/2, which is like multiplying by minus 2, and you'd write a squared plus x squared to the 1/2. Because it's minus 3/2 goes to minus 1/2, it's in the denominator, so it's 1/2 in the denominator. But then you also have to divide by the derivative of this thing with respect to x, so that's 2x. So it's lucky that that x is there to get canceled out. So we divide x by 2x, and we get a 1/2. So that's the integral of that thing, and then we evaluate it from L over 2, or from minus L over 2 to L over 2. And that's your I hat component. Okay. So we'll do the evaluation in a minute, and we don't want to get all of our fun here at once. Now, this other integral, you can't do as straightforward. You can't just bring that up to the minus 1/2 and divide, because you divide by minus 2x, and there's no x there to cancel it out. So for this, we're going to use a table. Meaning I looked up this integral in a table. So what we're going to use is that if you have the integral of, in this case, dx over a squared plus x squared to the 3/2 in the bottom, if you're in this case, that's equal to, we put an x in the top over a squared. Yes. X over a squared times a squared plus x squared to the 1/2 in the bottom. You may not believe it. If you don't believe it, take the derivative of this. It'll turn into that. Okay? You can go the other way. So that is actually true. I got that from a table. So if we apply that to this, then let's see what we get. Well, we have our k e lambda along for the ride. And this says we need to put an x up here. That's fine. And it says, but actually we had an a along for the ride as well. So let's go ahead and put that a there. Because you notice the a wasn't in here. It's just another constant that we have moving along. And then it says that in the bottom we have a squared, and x squared plus a squared, or a squared plus x squared, same thing, to the 1/2 in the bottom. Okay. So there we used that standard integral there. So that's also from minus L over 2 to L over 2. Okay? So now let's apply our limits and see what happens. That's j hat. So now we're going to apply the limits minus L over 2 to L over 2 and see what we get. So let's see, a lot of stuff's going to go away here. That and that go away. The 1/2 and the 2 basically cancel to make 1. So pretty much what we have here is ke lambda. I'll pull them out. And we're going to plug in L over 2 into the x, and we're going to plug in minus L over 2 into the x. So this is going to be 1 over a squared plus, that's L squared over 4 to the 1/2, right, minus, and then plug in minus L over 2. Okay, the ke lambda's out here, 1 over a squared plus minus L over 2 squared is again just L squared over 4 to the minus 1/2 to the 1/2 in the bottom, like that, I hat. Okay. Well, look at this. We have a term minus itself. It's 0. The whole thing made 0. So again, eventually we're going to make it over here, and that's 0 on the I hat. That tells us that the field has no x component. Okay. That one came out to be 0. Let's see. Hopefully this one won't be 0, because then we have no field. That can't be right. So let's write ke lambda. Let's pull out the constants. Ke lambda. And actually you'll notice that this cancels one of those. So everything's going to be over a. I'll go ahead and leave it on the inside, though, just because I'm that kind of guy. And now we're going to plug in L over 2 into x. So it's going to be L over 2 over a times the square root of a squared plus L squared over 4 to the 1/2 minus, and then we're going to plug in minus L over 2. So minus L over 2. And then the bottom is going to be a squared plus L squared over 4 to the 1/2, like that, j hat. Whew. Just enough room. Okay. So this whole thing, when we put it together, equals what? This was 0. 0 component on the I hat. And the j hat, it's not going to make 0, because this minus makes a plus. It's L over 2 minus minus L over 2. It's really L over 2 plus L over 2. It's L. The fact that we had an x here kept this one from being 0, because when you plug in L over 2's in an x squared, it's the same thing. So minus itself is 0. But when you plug them in with an x there, it's not the same thing. And that's what made it not be 0. So then we get plus ke lambda. This becomes L over what's left, a times the square root of a squared plus L squared over 4 j hat. So the answer is it does have a value in the j hat direction, in the y direction. There is a field. So this then is the answer. 0 in the x hat and that expression in the j hat. Okay? You could also notice that some books you might see it written as Q. They might set this whole problem up as a rod with a uniform charge, big Q. You could convert it to your own charge density, or you could see what is lambda times the length. That's the total charge on the rod. So if you have this in your textbook you're using and you see a big Q there, that's the reason. So you can think of it as a rod with total charge Q, or you can think of it as a rod with charge density lambda and length L. You can also look at this and realize it does make sense. It looks like Coulomb's law. It's K, Q, and this should have a unit of a length squared, and it does. Here's a length, and here is a length squared, square root, here's another length. So everything makes sense. Okay? It's a good way to check your answers that way. It's a good idea. So, question, let's see. Question this time is what? Prof SP, what methods can we use to solve the integrals? Okay, right. So for the y-axis integral, I went to a table, because it's not an integral I can just do manually. So I looked it up in a table. And the answer is you can use any method you want. Okay? This is not a calculus class. We're not making you memorize a bunch of definite integrals. So you can look them up on tables. You can look them up on your computer. You can do it on your phone. You can use Mathematica, whatever you want to do. For the exams, when we limit what materials you can use, we'll make a table of integrals available with all the integrals that you might need for the exam. So don't worry about memorizing definite integrals, at least for this class. Symmetry. Very important topic, symmetry. Physicists love symmetry, okay? If you ask them why, they'll give you some bullshit about the beauty of the universe and the nature of this and that's really not true. The real reason is that we're lazy and it makes problems easier to solve. So let's start with a good, simple definition of symmetry. When an object looks the same on both sides of an axis. Okay? When an object looks the same on both sides of an axis. So let's think about our charged rod problem that we just did. Here it was. It's a nice charged rod, charge density lambda. And the key was that this point that we were trying to figure out, the E field, was along the center of the rod. Remember? It was at 0, and we had a length L over 2 here, and a length minus L over 2 there. So this was a symmetric problem because along the axis that we cared about, the axis along which we were calculating the electric field, we had the same length of rod. It looks the same this way, and it looks the same this way. So by this simple definition, it was symmetric. Okay? So you say, so what? It was symmetric. Why are we excited? We're excited because of the lazy part. Let's add to our definition. We can use it to predict when something equals 0. Okay? We went into this problem and we thought about DEP and we calculated all the components, we did all these integrals, and it was a long problem. Half the difficulty was doing the x-axis and half was doing the y-axis. But let's think about it. If we had thought about symmetry, we might have realized that here is a dx right here. This dx is going to make a DEP like that. But what about the symmetric dx, the one over here? It's going to make a DEP like that. And they're also symmetric. The two DEPs look the same on both sides of the axis. But what about their x components? Their x components look like that, and if you add those as vectors, they cancel. So the two symmetric dx's will have canceling x components of the DEP. And you could say, well, what about this dx way out here on the end? It also has a symmetric dx. It would create a field, DEP kind of like that, and a DEP kind of like that, and its x-axis component would be that, its x component would be that. Any dx you come up with on one side has a dx on the other side that is symmetric. They make symmetric vectors, and the x-axis always cancels. So basically, by symmetry, we could have known ahead of time that, that EP is going to have a 0 on the I hat. And then we would still have to solve the j hat. So the problem could have been 50% easier. We could have just completely ignored the x hat without even starting, just by looking at it and saying, oh, well, it's symmetric. Don't worry about the x component. Okay? Another example then, let's think about this. Let's think about a ring of charge. Let's do a problem really fast with symmetry. Okay? Here's a circle, and it's basically a rod of charge that has been bent into a circle. It's got a charge density lambda going around the circle. So the total charge would just be lambda times the circumference. The question is, let's calculate the E field at the center. Okay? What is EP? Well, you can imagine we could break it up into little dx's going around. We could write Coulomb's law. We could do all these integrals. We could do all this stuff, but there's really no point because I know that it's going to be 0 by symmetry. Because for every dE or every dx here that has some q, some charge, dq, that's going to create a field that way. And there's a symmetric one here that's going to create a field that way. And the two are going to cancel. For every one here that creates a field that way, there's going to be one here that creates a field that way. And the charges are going to cancel, or the fields are going to cancel. So you can instantly say that the E field in the middle is 0 because you're at a point with a certain symmetry. Okay? It doesn't always make everything 0. Right? You can't just say symmetry 0. You got to think a little bit about how it makes something 0. Another way to think about it is you can think about explicitly about all the little dx's and dq's making vectors and what adds up. Another way to think about it is something is 0 when there's no way to know which way it would point. Okay? So if you looked at this point and thought, which one is going to be 0, it has to be the x component because there's no reason that the x component would point left or right. Okay? Is the E field going to be to the right or is it going to be to the left? Well, there's nothing special about right or left. Right and left are the same. Therefore, that's the part that's 0. Here, is the E field going to be up or down or right or left? In this case, no direction is special. Whenever a direction is not special, that's the one that's going to be 0. Okay? So symmetry, they can't give you a mathematical law of how to use it for this class, but you can definitely use it to make problems easier and speed them up. Okay? And it can save you a lot of time. Had we made one little mistake calculating EX, we would not have gotten 0 and would have got the problem wrong. So it would have been much more efficient and safe to simply say it's 0 by symmetry. Another way you can use symmetry is to break it. You just got it. Like a cheap toy, let's break it within minutes. Okay? These are the kinds of problems with broken symmetry we can use to help you think about symmetry, like on the homework. For instance, here's a ring of charge with a little piece missing. So without doing any calculations, you could say, which way is the field at point P in the center? You don't have to do any calculations to know that it's this way. Okay? Because you can think about all these dx's canceling. The one that doesn't have anything to cancel is right here. So as long as the charge is positive on the ring, the field would have to be that way. All the other components will have their things cancel. But this component here is missing its partner over there. So E is going to be to the right. Okay? That's an example of broken symmetry. Another case of broken symmetry is we could do the rod and not put the point at the center. Okay? This is another key thing to realize. The rod is very symmetric in and of itself. You can draw an axis of symmetry through the rod like this. That's a symmetric axis for the rod. You can draw an axis of symmetry here. That's a symmetric axis for the rod. But it has to be the axis you're using in the problem. If you put your point P here, there's really no axis you can draw that's symmetric. You're probably going to do the problem like this and think about these dx's and these dx's. And then you're not on an axis of symmetry, so nothing's going to be 0. The x component is not 0, the y component is not 0. You could kind of look at it and we could ask, is the field going to point more or less to the right or the left? Just worrying about the x component. And in this case, you look at it and say, well, there's more on this side than that side, so it's going to point. Something like that. Okay? So use symmetry to make hard problems easier and use it to think about the direction of a field. We'll use it for many more things later, but that's your introduction just to start thinking about symmetry.